Welcome back. The kids of Decalen Primary and their teacher, Dominic Smith. Good morning, guys. I hope you guys are well.
Good morning. Morning.
It's a great time for particularly Dr. Chris Smith to speak to our kids. Let's just talk about firstly, Chris, before we get to the kids, the importance for you. And of course, we get great questions week in and week out from our older listeners. But what does having particularly questions coming from young people and young children, what does it mean to you as someone who is trying to promote science, technology, education, not just where you live in the UK, but around the world?
Well, when I was little and somebody who was a scientist or something would come to my school, I used to love talking to them because I could ask them anything. And I used to have a brain bursting with good questions. And I used to have the best days when you had the chance to quiz people and just get them to answer those questions that you'd thought up, that often you'd ask your parents and they'd say, "Dunno, ask your teacher." So this is one of those opportunities for the young me to reach the new young me and address questions that people have and want to know the answer to.
Excellent. Okay. Dominic, I want you to get Caden Abner ready, but first up, Alex Pillay. Is Alex Pillay there?
Yes, I am here.
Hi, Alex. Dr. Chris is listening. Fire away.
How did they determine that the sun emits all colors of the rainbow, and why do they call this combination white light?
Hello, Alex. Well, this goes back to Isaac Newton, actually, who was one of the first people to realise that light is waves and that the white light coming from the sun is a combination of different colours. And his experiment was to pass the light from the sun through a prism and split the light up into all the different wavelengths or colours. And the way this, or reason this works, is that when light goes from one medium, in other words the air, into another medium, the glass in a prism, it changes speed. But different sizes of waves change speeds by different amounts. And when they change speed, they bend their course a bit. So this has the effect of spreading the wave colours out and separating them. And that's what Newton realised, that you could bend the light, change its speed, change its course, see the different colours, and if you brought those colours back together again in another crafty experiment, you could return all the separate colours and make white light again. So his insight was that what we call white light is merely our brain's perception of seeing or experiencing all those separate colours all at once, but actually the light we call white light from the sun doesn't exist as white light. It is a mixture of all those different colours together, and when they stimulate your eye the way they do, we call that white light.
Let me weigh in here, Chris. Why is it then like the light that we get from the sun, known as white light, and through a prism, they scatter and you see various colors. But why is it then that if I take the rainbow palette of finger paints in front of me and I'm mixing it all together in equal amounts, why does that collection then of colors gravitate to being a darker, if not blackish color?
It depends whether you're using additive or subtractive coloration. If you are absorbing colours to make a colour, so in other words, I'm looking at a blue wall. The reason it's blue is because it's absorbing all the different colours of the white light hitting it, and it's only reflecting back the blue. So if I take that blue, and now I take the same colour I would use to make red on a wall that absorbs everything apart from red, and I take the same colour that makes green on a wall that absorbs everything and makes the wall look green because the only thing that comes back is green, if you add all that together, you end up with a combination of chemicals capable of absorbing all the colours of the spectrum, so there's nothing to reflect back at you, so it looks dark or black. But the opposite is if I take snow as an example, which is lots of little ice crystals, they reflect because the light is hitting crystals of all different shapes and sizes, and the light has travelled different distances into the snow, it will reflect all the different colours back at me. It's not removing anything, it's reflecting everything. So it's the difference between making a colour because of what you reflect off and what you reflect back that you haven't absorbed, and that's why your palette looks darker as you mix more colours together, whereas snow looks white.
Let's go to Caden Abner now. Dominic, Caden, good morning. How are you?
Hello. I'd like to inquire on why time moves in only one direction.
You sound like an adult, Caden, sitting in an office and an important call just came in. How old are you?
I'm about 12 now. I'm turning 13 in October.
Of course, that age, I'm 12 and a half, I'm almost 13. You get the question there, Chris?
Yeah, I thought Caden was phoning a friend for a minute, but there we are. And it wasn't me phoning a friend. The answer to this question about time is that the universe started about 13.8 billion years ago with the Big Bang, and it has been growing ever since. And as it grows, it moves from a tiny point, which is infinitesimally small and full of energy, to something which is much more spread out and much more randomly distributed. So you've gone from a state of order, where something is all in one place all at one time, to something which is spreading out all the time to become much more disorganized. And that is an increase in entropy. And the insights of a great scientist over 100 years ago, Boltzmann, was that everything that happens to lead to an ultimate increase in this concept we call entropy. And so you can think of time as almost like an increase in entropy. As things move forward, they're moving towards more disorder. This is more favourable for the reaction to happen. It's leading to an increase in entropy, and that is the forward movement of time. Now, time doesn't have to tick at a fixed rate, though, remember. Just because time is moving forwards, and we don't think that you can reverse time, we don't think that we can go backwards in time, and Stephen Hawking famously said, I don't think time travel could exist because otherwise we would have been invaded by tourists from the future. But you can still change the rate at which time ticks, and we've got evidence for that happening all the time. Your feet are closer to the Earth's centre of mass, its centre of gravity, than your head is. Therefore, your feet are feeling a more intense gravitational field than your head is, and therefore your feet experience time at a different rate from your head, because gravity affects the rate at which time ticks. Speed affects the rate at which time ticks, and the satellites whizzing around the Earth's surface, which are doing GPS so we can navigate with a GPS navigator in the car, they are going much faster than you are at the Earth's surface. And because of that approximation much of greater speed closer to the speed of light, time changes for those satellites compared to us on the Earth. And so when the signals come from the satellites, we adjust the time signature in order to compensate for the fact that time is passing faster for us than it is for them. And so time does tick. It does tick forward. It doesn't tick backwards, but it doesn't always tick for everyone at the same rate. And that was the great insight of Einstein and his theory of both special but also general relativity.
Does that mean theoretically, and even though we don't notice it because the fractions are so almost minute, that we are theoretically use the example of our feet and our head being affected by gravity and times, we are theoretically already time traveling?
In some respects, yes, your feet are ahead of the game because they're experiencing a more dense gravitational field. Your feet are actually going faster in time than your head is, so your feet are older than your head.
Well, what happens if your feet is constantly in your mouth? So that's when you find some maybe.
Well, if you're very,
some
very
equivalent.
short, then it's less of a problem for you. But if you're very, very tall, then your feet are racing ahead in time. And for them, time is travelling at the same speed that it is for your head. But if you were to bring the two back together, you would find the cells in your feet had aged at a slightly different rate from the cells in your head.
Dominic Smith, grade 7 teacher at the Kalen Primary. Could you please line up Mika van Skalkwyk for me, please? Good morning, Mika. Go ahead, fire away with your question to Dr. Chris Smith.
Why don't birds get electrocuted when they land on electrical wires?
Oh, hi, Mika. The answer for this one is that an electrical wire is at a high voltage potential compared to the negative wire or the earth. But electricity flows when it can complete a circuit and go from an area of high potential to an area of low potential. Now, when a bird sits on a power line, it's got 2 feet on the power line, but there's no potential difference between its 2 feet. They're both in the same part of the wire, and they're both at high voltage. There's no low voltage for the other part of the bird to act as a conductor between. So there's nowhere for the electricity to go. So the bird does not act as a conductor. And to be electrocuted, you have to have electricity flowing through you from that high potential to the low potential. Now, if the bird, as it took off, touched its wing against, say, part of the pylon that's supporting the cable, then there would be potentially a route from the high potential in the cable to the earth, and the bird would be a conductor and it would get fried. But because the bird is just staying where it is on one part of the cable, There is no potential difference between the bird and the cable, and therefore there's no flow, therefore there's no current, and therefore the bird is absolutely fine.
Excellent. Up next, we have Sade Epner. Dominic, good morning. Sade, how are you?
Fine, and yourself?
Very, very good. You have a keen interest in math, science, technology at school at the moment?
Yes, I do.
Yes, you do. What's your question to Chris?
My question is, how do airplanes stay up while defying Newton's law of universal gravitation?
Hi, Sade. The answer to how an aircraft flies is that it's Newton's law that for every action there's an equal and opposite reaction. So if something is pushed along, then it feels a push in the opposite. It makes a push in the opposite direction. How does that happen? Well, as an aircraft goes along, it's got wings. It pushes air downwards, and if you push air downwards, the air pushes back on you equally hard, and so you get lift or go upwards. So the simple answer to your question is aeroplanes have wings. Those wings push air downwards. If you push air downwards, it pushes you upwards just as hard. Now, the slightly more subtle answer here, and this is where it gets slightly more complicated, but it's fairly easy if you follow it through. The wing is a curved shape, and the front of the wing is slightly higher than the back of the wing. This means as the aircraft is pushed through the air by the force of the engines, the air that travels across the lower surface of the wing is going from high to low. So the air is being pushed down by the wing, so the air pushes up on the wing, and that gives you lift. You also get some lift from the top surface of the wing, and this is because the wing is curved, and as air goes over a curved surface, any fluid going over any curved surface will stick to that surface, and that's called the Coanda effect, after, I think his name was Henri Coanda. I think he might have been Romanian or Croatian. But the bottom line is, as the air is travelling over the top surface of the wing, it is being pulled down to stick to the top surface of the wing. And as you've guessed it, if you pull air downwards onto the wing, the air pulls you back upwards. So you get lift from the bottom of the wing by pushing air down. You get lift from the top surface of the wing by pulling air down. The net effect of both is that the air gives you a push in the upwards direction. That gives you lift. And as long as the aircraft keeps on powering its way through the air, it will keep generating lift, which, once all things balance out, if you're going at the right speed, you will end up with the acceleration due to gravity that's trying to pull you down, matched by the lift that you're generating that's pushing you up, so the plane stays at a stable altitude.
Let's get up Brighton Pahua up for our next question. Good morning, Brighton. How are you?
I'm fine, thank you. And yourself?
Very good, sir. How old are you?
I'm 13.
Excellent. Go ahead. Fire away with your question.
Okay, my question is, why is it not possible for two different species to reproduce and create a new species?
Hi, Brighton.
Yes.
The answer is that under certain circumstances, it is possible. Closely related species can still interbreed, and there are species of butterfly that do this. There are species of mammal like lions and tigers that do this, horses and donkeys that can do this. But what unites all of those is they've got to be really closely related. Animals that are more disparately related, or not even related at all, are not interfertile. They can't crossbreed with each other, at least not easily and not without perhaps some scientific help, because the structure of the chromosomes in those animals is different. Humans have 23 pairs of chromosomes. I think sheep have 54. And dogs have a totally different number again. Horses have a different number again. And elephants and mammoths have slight differences as well. So when cells are trying to mix their genetic material together, for instance, when you have a sperm from dad and an egg from mum, dad has put half of his chromosomes in the sperm and the mum has put half of her chromosomes in the egg. When they come together and you fertilise the egg with the sperm, if you haven't got the right number of chromosomes in there to make the complete number that the healthy animal would have, it's not going to work properly, because we know that you have to have the right amount of genetic material with the right copy numbers of all the genes to make the cells work. And if that doesn't happen, then the cells aren't going to be viable. And so when animals that have different structures of their genetic material tried to breed, they would end up with progeny or offspring that had the wrong genetic makeup, and it would just not work. And as a result, the animal wouldn't develop and it would die before it even got started. So this is the reason why species do not crossbreed. And in fact, it's very useful if you think about it, because if that were happening, it would make the process of evolution and specialization very, very difficult, so that it would be harder for animals to segregate into different types that could exploit different environments and develop unique skill sets that made them much more successful as entities. And I think that's probably why we've ended up in the situation we have, with species that are pure breeding and don't cross-fertilize with other disparate species. Imagine if plants and people could sort of hybridize, and you'd end up with some very weird stuff going on, wouldn't you?
I know a couple of wallflowers, uh, Chris, but that's besides the point. Let's go to Kira Peterson. Good morning, Kira. Are you there with us?
Yes, good morning.
How are you?
I'm good, and you?
Very good. Fire away.
My question is, how do X-rays work?
Hello, Kieran. The answer to this one is that X-rays are a form of light, just like the light coming from the sun that we can see. But unlike the light coming from the sun, X-rays are waves which are much closer together. And because they're much closer together, when they go to you, unlike light that we can see, which bounces off, they can thread their way between all of the particles that make up your body and come out the other side. So if we put something which is sensitive to X-rays, and in the old days they used to use photographic film, nowadays we've got electrical detectors, the X-rays that come out the other side can be picked up, and we can measure how bright the X-rays are in each position. And some parts of your body are more transparent. In other words, they are more like window glass to X-rays than others. And this is because some chemicals get in the way of X-rays and do stop them a bit. Bones, for example, have got a lot of calcium in, and this soaks up X-rays. So if we measure how much X-ray radiation comes out the other side of your body, we can then work out where the parts are that are denser and have more things like bones in them, and more parts which are less dense and have got things like lung tissue with gas in it that doesn't absorb any X-rays, and we can then build a picture of where the dark spots and bright spots are, and that corresponds to areas in your body that are denser because they have more bone or more tissue, and less dense because they've got, say, more lung tissue. And as a result, you can get an internal picture in 2 dimensions, admittedly, of what the body looks like when you shine X-rays through. You can do even fancier stuff now. For the last few decades, we've been doing what's called CT scanning, and what that is called computed tomography. And this uses a whole load of X-ray pictures which are shot from different directions all around in a big circle around the body, and it brings all of the different shots together, and it can build a 3D model of what the body looks like inside. And so we sometimes use that to get a better idea as to the structure of something going on inside the body if we need to see it in 3 dimensions.
Final question this morning, Caitlin Henry. Good morning, Caitlin.
Good morning.
Go ahead. Chris is listening.
Okay. My question is, why are antibiotics effective towards bacteria but not towards viruses?
Okay, Lynn. The answer is that bacteria are cells. Our body is made of about 37 trillion cells, and these are individual entities that have genetic material in them and a membrane around them, and they grow and they die. They are their own thing. Bacteria are the same. They have a cell wall around the outside, genetic material in the middle, and they can grow, they can reproduce, and so on. A virus is about 1,000 times smaller than a bacterium, because viruses are so tiny they don't have anything in them apart from just their genetic material. So viruses need to go inside one of our cells or even a bacterial cell and use the chemicals and the machinery to make new viruses. The way antibiotics work is that they exploit differences between how our cells look and how bacterial cells look. Because there are some things in bacteria that are not in our cells, if you make antibiotic molecules, they can latch onto those things and destroy them, and so the bacterial cells die. Because viruses are not effectively alive, they're just an infectious bag of genes that have to go into our cells or into a bacterial cell to grow. They don't have any of those structures, and so you can't have antibiotics that kill a virus because those things don't exist in the virus. But we do have antivirus drugs these days, and there's a whole slew of drugs that treat HIV. There are drugs that treat things like the herpes simplex virus that causes cold sores, and other drugs coming along now to treat a whole host of other viruses as well. So there are Drugs are a bit like antibiotics for viruses, but they tend to work in quite a different way than antibiotics that kill bacteria, which exploit the differences between bacterial cells and our cells.
Dominic Smith and the Decalen kids, really appreciate your time. Thanks so much for joining us. Bye for now. Also, Chris, really appreciate you. Next week, our listener questions back again. Everyone, guys, thanks so much for joining us again. Have a great weekend.